This video is about finding relative extrema of functions of two variables. We will define relative extrema for functions of two variables. We'll talk about what critical points are. We'll talk about what they were in Calculus 1. We'll review that, and then we'll extend that idea to define them for Calculus 3. And then we'll talk about finding relative extrema. We will review the first derivative test from Calculus 1, and then we'll extend it to functions of two variables in Calculus 3. Now, the methods that we're using in this section can be extended to functions of n variables, but the second partials test would have to be modified in that case. We'd have to have a lot more different cases if you had a function of, say, 3 variables or 4 variables or n variables. So everything that we're going to discuss here is really just for functions of 2 variables. There is an extension to n dimensions, but it's a little bit more involved, unfortunately. So let's talk about optimization. That just means finding mins and maxes, trying to find a relative min or a relative maximum value of the function. And remember what those terms mean: relative or local minimum, or if you had more than one, it would be minima, of a function of one variable. In Calculus 1, a relative or local min was the function value on the graph. It's a y value at a particular x value. If that function value is the lowest y value nearby, so all of the other y values nearby are greater than or equal to f of x naught. In that case, f of x naught is a relative min or a local minimum. Graphically, you might see something that looks like this. Like there is a relative min, there is another relative min, because all the y values nearby are larger than that, and all the y's over here nearby are larger. So I'll say for x near x naught, and when I say near x naught, I just mean on some interval nearby. And you can stop making that. You can stop the interval when it no longer when this statement is no longer true. So that's what we said in Calculus 1 for a local minimum. And when we're talking about a local or relative maximum in Calculus 1, well, that's when the y value we're interested in is greater than or equal to all of the y values nearby. In this picture, there we've got a local maximum because all the y values nearby are smaller than that y value. So that is a min or a max in Calculus 1. Well, with functions of several variables, the idea is exactly the same, except instead of looking at y values and comparing them to other y values nearby, we're going to look at z values and compare them to other z values nearby. So a relative min for a function of 2 variables is just a z value. Maybe it's a z value that occurs at x naught, y naught. If this z value is less than or equal to all of the other z values nearby, let's say for x, y near x naught, y naught, then this number is a relative min. Or if you have a z value, f of x naught, y naught, and it's greater than or equal to all of the z values nearby, So it's the largest z-value in the neighborhood. That's a relative max. If it's the smallest z-value in the neighborhood, that's a relative min. Now, these are particular values, like that's a number. So you're substituting in x naught, y naught. You're just going to have a number there, and this is a number. And these are z-values. For every x, y, you get a different z-value. So all the other z's are less than or equal to this z and when we have a relative max, or all the other z's are greater than or equal to this z when you have a relative min. So it's just the same thing as it was over here. We've just extended it for functions of two variables. Now, if I want to find the potential minima and maxima, those are together, those are called extrema. If I want to find potential relative mins and maxes, in Calculus 1, we found what were called critical points. Now, being a critical point, or a critical value of the function, did not guarantee that the function was optimized there. A critical value of the function is just a potential location of a relative min or a max. So a critical value from Calc 1 is an x value in the domain of the function that satisfied the following. I'll just say for which f prime of x naught, that being our critical value, is 0, or f prime of x naught is undefined or does not exist, because derivatives are both limits and functions, so we can use undefined or does not exist. Either one is okay. All right, so let's look at the graph of a function and point out all of the critical values. So maybe you've got a function that looks like this. I know I'm doing a lot of weird stuff. That's totally fine. Okay, now let's point out all of the critical values. Well, we've got critical values wherever the derivative is 0. It looks like I've got a 0 slope right here. Remember, the derivative is the slope, so whenever we have a horizontal tangent line, that's where our derivative is 0. So the x value that goes with that 0 slope, that's our first critical value. I'll call it x naught. Here's another one. That's x1. Looks like we've got another one. I'll call that one x2. I'm just going to number these. There's x3, where the derivative is undefined. x4, another 0 slope. x5, maybe that's not exactly x5, maybe x5 is more over here. x5, 0 slope, undefined slope. x6, looks like there's a 0 slope there. x7, and it looks like it might flatten out, I'm not sure, but I don't see any 0 slopes, I just see negative slopes. So it looks like we've got 1, 2, 3, 4, 5, 6, 7, 8 critical values. Now, those that correspond to relative maxes, let's write those down. Now, remember, the x value isn't the maximum, relative maximum value of the function. The y value that goes with that x value, that's the relative max. If I asked you for the maximum height, let's say you threw some object in the air and I wanted to know the maximum height, you wouldn't tell me what time it was when it was at the maximum height. You would actually give me the height. So we're not interested in the value of the independent variable, we're interested in the value of the dependent variable. We're interested in the y. Not the reason, but the y value on this graph, y equals f of x. So the relative maxes are f of x naught, that's a min, f of x sub 2, that's a min, f of x sub 4, that's a min, f of x sub 6, and f of x sub 7. And we have relative mins at x1, and x3 and x sub 5. And I think that's it. Now every critical value on this picture corresponded to either a min or a max, but I could have drawn a different picture. Let me draw a couple of pictures where you've got critical values that are neither mins nor maxes. So maybe you've got a critical value for a function that looks like this. I didn't do a very good job drawing it, but it doesn't look like a zero slope. Let me make it a little flatter. It's very exaggerated. Okay, so at this point, we've got zero slope. So we would have a critical value right there at x1. But that's neither a min nor a max because it has a negative slope, then a zero slope, and then a negative slope again. It's not the smallest y value in the neighborhood because there are smaller y values to the right. It's not the largest y value in the neighborhood because there are larger y values to the left. So this is a critical value. But f of x1 is neither a min nor a max. Now we could have also had something that looks maybe like this. So we had a flat spot that was not a critical value, or excuse me, that was a critical value that did not correspond to a min or a max. It's also possible that we could have a sharp corner. Maybe you've got a graph that looks like this, piecewise linear graph. It's increasing, and then it's increasing at a slightly different rate. At that x value, the derivative is undefined because we've got a sharp corner. We've got one slope on the left and a different slope on the right, so the derivative can't be defined at that transition point. But x1 is still a critical value. So x1 is a critical value. And f of x1 is neither a min nor a max. Okay. But let's remember the definition from Calculus 1. Critical values. These are potential locations of relative mins and maxes. These are x values in the domain, and the domain is very important. That's critical. It was an unintentional pun. And we need f prime to equal 0 or f prime to be undefined. Now let's think about the Calculus 3 analog of that. I've got a surface now. It's got little hills and valleys. The question becomes, when do we have a relative min or a max? Or where could we possibly have a relative min or a max? Well, that will happen every time we have a horizontal tangent plane. So critical values correspond typically to horizontal tangent planes or places, locations, xy pairs, where the tangent plane is not well defined. So here is our Calc 3 definition of a critical value. So critical values, or I guess we should call them critical points now. We also called them critical points in Calculus 1. But these are different. These are actually xy pairs. This is our critical points are points of the form x naught, y naught in the domain of your function. Such that the gradient at that point is the 0 vector, or the gradient at that point is undefined. So again, they have to be in the domain. We can't have a min or a max at a point that's not in the domain. But instead of having the derivative equal to 0 or the derivative being undefined, we use the gradient vector, which makes perfect sense because I told you before, the gradient is our multidimensional analog of the first derivative. It's the vector of first partials. If your function has two variables, it's a vector with two components. If it's a function of three variables, it's a vector with three components. But it's just the vector of first partials. That's all it is. Now, if this gradient vector is 0, remember what that's saying. It's saying this. And some students miss it. So make sure you pay attention here. If the gradient is 0, that means that the partial of f with respect to x is 0, and the partial of f with respect to y is 0 at the same time. So this is a system of equations. This is a system of usually nonlinear equations that you'll need to solve for x, y. So you've got to simultaneously solve both equations for x, y. Those are your critical values. And any x, y in the domain for which these partials are undefined, those are your critical values too. So before we look at the rest of the test, the rest of the second partials test for finding relative extrema of functions of two variables, let's just find some critical points for a particular function. I thought I had my example right here, and I apparently wrote it somewhere else. I don't know where that piece of paper went. That's okay. So we're going to find the relative extrema of this function z. And actually, I'm going to use the same function that we used in class. We had x squared times, or plus 3y squared, times e to the negative x squared minus y squared. Wow, that's a function. It really is. We want to find the relative extrema of this. It'll probably take us the whole video to do that, and that's okay. The first thing we do is we find the critical values. And the way you find critical values for a function of two variables is you find the gradient vector, you set it equal to 0, and solve for x, y. And then, of course, you think about where the gradient is undefined as well. So you want to find any x, y in the domain for which the gradient is undefined. Once you've done that, and that, you have found all of the critical values. So the first thing we need to do is find the gradient. So I need the vector of first partials. It's a partial of f with respect to x times I hat plus the partial of f with respect to y times j hat. So I'm taking the derivative of this with respect to x. Okay, I've got a function of x times a function of x, so I'll have to use the product rule. Here's my first function, and there's my second function. According to the product rule, we have derivative of the first with respect to x holding y constant, so we get 2x, times the second, undifferentiated, plus the derivative of the second times the first. And the derivative of the second requires a chain rule. Derivative of e to some power is e to that power times the derivative of the inside with respect to x, treating y as a constant by the chain rule. So we have the derivative of the inside with respect to x is a negative 2x minus 0. So that's derivative of the second and we're multiplying that by the first. Okay, now we want to set this equal to 0, and we want to solve a system of equations. So the easiest way to do that is to factor this. So I'm looking at this and I'm thinking of this as a term and this as a term, because it's all, this is being added to all of this. And I want to factor out anything that they have in common. And it's clear that they have a 2x in common, and they also have the exponential in common. So we'll factor that out, and we say to ourselves, this times what gives us this first term? Well, they're the same, so I just multiply it by a 1. And then this times what will give me the second term? Well, that's taken care of. The negative is still there, so I have a negative times the quantity x squared plus 3y squared. So I think I'll just leave it like that. That's my partial with respect to x. Now to find the partial with respect to y, we do the same thing all over again. We've got to use the product rule again because I've got a function of y times a function of y. So this is my first function and that's my second function. So we get derivative of the first with respect to y, treating x as a constant. So we get 0 plus 6y. Derivative of the first times the second plus the derivative of the second. Derivative of e to some power is e to that power, times the derivative of the inside with respect to y. I'm treating x as a constant, so that's negative 2y, times the first, undifferentiated. And again, we want to factor out anything that these guys have in common, and I see the 6y and the 2y, so I can factor out a 2y. They also have the exponentials in common, so I've got 2y times e to the negative x squared minus y squared. And I say to myself, okay, this times what will give me this? Well, to get a 6y, I need a 3. And this times what will give me this? Well, I need the negative and that quantity. So I have negative quantity x squared plus 3y squared. All right, so I've got a simultaneous system of equations that I need to solve. This partial, which is this, has to equal 0, and this partial must be 0, and they have to be 0 at the same time. Now I've got 3 factors for each of these. I've got this times this times this. In order to figure out all the possible critical points, I need to set each of the factors equal to 0 and think in cases. So the partial of f with respect to x could be 0. If this is 0, this is 0, or this is 0. So case 1, here's our first case. We'll say partial of f with respect to x is 0, and let's say it's 0 because the first factor is 0. So it's 0 because that's 0. If that's 0, that means x equals 0. So I've got x equals 0 now. So in that case, the partial of f with respect to y, well, if x is 0, it would become this. I have 2y times e to the, that's 0, minus y squared. If x is 0, I've got 3 minus 3y squared over here. And I'm setting this equal to 0 and solving for y. Now, this product is 0 if one of these factors is 0, so either 2y equals 0, or the exponential equals 0, or 3 minus 3y squared equals 0. Well, 2y equals 0 when y equals 0. Exponentials are never 0, so that's not happening. We don't have to worry about that. If you don't remember, that's okay. Just remember y equals e to the x looks like this. No matter what x is, the values of e to some power are always positive. There's no way we can get 0 out of that. Even if that is a negative, or even if the exponent is negative, Remember what happens if the exponent is negative? Then it just goes that way instead if the exponent's negative. Maybe that's the graph of e to the negative x. But notice that the values of the function are never 0. We never cross the x-axis. So since that's never, the values of e to the negative y squared are never 0, we don't have to worry about that. This guy could be 0 whenever 3 is equal to 3y squared, which means 1 is equal to y squared, which means y equals plus or minus the square root of 1, which is plus or minus 1. Okay, now that was our first case. We said this will be 0 if the first factor is 0. So if x is 0 and y is 0, we've got a critical point. And if x is 0 and y is equal to plus or minus 1, we've got a couple of critical points. So we've got a list going. X is 0, y is 0, x is 0, y is 1, and x is 0, y is negative 1. Okay, so that's one way the partial of f with respect to x could be 0. Another way is if this exponential is 0. Remember, exponentials are never 0, so that's not going to happen. The third way is if this factor is 0. Now that's on a curve. That's actually it's actually an ellipse in the xy plane. So the second way that the partial of f with respect to x could be 0 is if this factor is 0. So 1 minus the quantity x squared plus 3y squared is 0. Or alternatively, you could say we're on the curve where 1 is equal to x squared plus 3y squared. That is an ellipse. So okay, so if we're on this curve, we also need, that means this is 0. And we also need this second factor, the partial of f with respect to y, to be 0 as well. So in that case, partial of f with respect to y is this. We've got 2y times e to the negative x squared minus y squared times 3 minus the quantity x squared plus 3y squared. And we need that to be 0 at the same time. Well, if we're on this curve, x squared plus 3y squared is 1. So this is actually just a 3 minus a 1. It's just a 2. So I've got 2 times that 2y is going to give me a 4y times the exponential equals 0. Okay, the exponential is never 0. So if this times this equals 0, that means 4y must be 0, which means that y must be 0. It's the only way it happens. So if we're on this curve and the partial of f with respect to y is 0, then we know y must be 0. Now if I know y must be 0, I can substitute that back in up here and find the corresponding x values. So if y is 0, we get 1 equals x squared plus 3 times 0 squared, so that's gone. So x equals plus or minus the square root of 1, or plus or minus 1. So we've got 2 more critical points. When x equals 1, y equals 0. And when x equals negative 1, y equals 0. So we've got 5 horizontal tangent planes. Z is just equal to a constant on each of those tangent planes. And now our job is to figure out, well, do each of those points correspond to mins, to maxes, or something else? Okay, that was tough. Now, again, remember, if you have a partial of f with respect to x and a partial of f with respect to y that factors, you've got to think about all of the different ways that this could be 0 and this could be 0. Whenever I give this question on quizzes and tests, students really struggle with finding the critical points. They might find 2 of them, but they might have trouble finding all 5. Usually one that has 5 will probably not be on a quiz or a test. Maybe you'd have a problem that has 3 or 4 critical points. Okay. All right, so now we want to go back to finding relative extrema from all this. We found the possible relative extrema, the possible locations of the extrema. How do we determine if we've got a min or a max? Well, back in Calc 1, we had 2 tests. We had the first derivative test and the second derivative test to determine if extrema corresponded to, to determine if critical points corresponded to extrema. Now the first derivative test had to do with the first derivative changing sign. So if the first derivative went from negative to positive or positive to negative, you had either a min or a max. We don't want to worry about that here because we've got infinitely many directions now. There's not just a left and a right of some x value anymore. So that really doesn't make sense. It doesn't make sense to try to generalize that to functions of several variables. But we can generalize the second derivative test. So let's review the second derivative test. Now let's say you're at a critical point. And we're at a critical point where the first derivative is 0 so that we can take a second derivative. So we'll say the first derivative is 0, so we're at a critical point, and the second derivative is positive. Well then, remember what that means. This means you have 0 slope because the first derivative tells us the slope of the graph at that point. And if the second derivative is positive, that means the graph is concave up or concave upward. So if the first derivative is 0, second derivative is positive, your graph looks like this. You're at the bottom. So that means that f of x naught is a relative min. A lot of students have trouble with this because they say, oh, when the second derivative is positive, it's a min, and it seems like positive should correspond to max and negative should correspond to min. No, don't do that. Interpret it this way. Second derivative is positive means it's concave up, then just look at your picture. If it looks like that and you're at the place where there's 0 slope, of course you're at a min. Remember, second derivative positive means the graph is concave up, and that's enough to get you that f of x naught, f of that critical value, is a min. If the first derivative is 0, so we're at a critical value, and the second derivative is negative, well, that means our graph is concave downward. We're at the top, so f of x naught must be a relative min. And remember what we said in Calc 1. If the first derivative is 0 and the second derivative is 0, the test is inconclusive. Try something else. And that might happen if you have something, you've got lots of derivatives that are 0. It might be like on a graph like something that looks like y equals x to the 4th. Or the derivative of x to the 4th is 4x cubed, and the second derivative of that is 12x squared, and we just keep getting 0 because the power of x is so high. It has to do with the multiplicity of the 0, so let's not worry about that right now. But if the second derivative and the first derivative are both 0, the test was inconclusive. Now, in Calculus 2, we can't talk about this exactly, but we've got two directions. We've got the x direction and the y direction when you're talking about a function of two variables. So I said Calculus 2. I meant with functions of two variables in Calculus 3. Saying all the wrong things today. It's okay. Yeah, we can do something analogous to this. Analogous. Never really sure how you're supposed to pronounce that. Anyway, we've got what's called the second partials test in this case. Now, I told you before that the gradient of f is our multidimensional analog of the first derivative. We don't have a first derivative anymore But we've got this, it's a vector of first partials. And you got to be happy with that. That's as close as we're going to get to a first derivative in this class. And we see that it's behaving like the first derivative. In order to find the critical values, we need this vector to be 0. Just like we needed the derivative to be 0 before, now we need the gradient to be 0. That's our first derivative. We've also got a new analog for the second derivative. The multidimensional analog of the second derivative is a matrix. This is called the Hessian matrix. Normally just the Hessian. You don't really say matrix afterwards typically. If you have a function of two variables, the Hessian looks like this. You take the partial with respect to x first, and then you take the partial with respect to x again, and then with respect to y. Or you take, in the second row, you've got the partial with respect to y, and then you take its derivative with respect to x, and then with respect to y. That's the Hessian matrix. This is the matrix of second partials. Now, if we had a function of three variables, your Hessian matrix would still have second partials in it, but you'd have to take partials with respect to x first, and then with respect to x, y, and z. And then the second row, you take the partials with respect to y first, and then with respect to x, y, and z. And the third row, you take the partial with respect to z first, and then with respect to x, y, and z. But we're going to focus right here for this class. And of course, if you have a function of n variables, this is an n by n matrix. But with a function of two variables, this is a 2 by 2 matrix. This is our new second derivative. So that's our gradient. It's the analog of the first derivative. It's a vector of first partials. And then over here, this is called the Hessian. It's the analog of the second derivative, and it's the matrix of second partials. Now remember, second partial with respect to x gives you slope or concavity in the x direction. Second partial with respect to y gives you concavity in the y direction. And then these tell you how slopes in the x direction and y direction change as you move a little bit in the perpendicular direction, the direction given by the other variable. We're not going to worry about that right now. Okay, so say to yourself, well, what's the multidimensional analog of that? Well, let's talk about it. You're going to take your Hessian and you're going to substitute your critical values. And then you're going to compute the determinant. The determinant of the Hessian actually, I'll write it like this. At a critical value could be represented this way, or it looks like an absolute value. It's not an absolute value though, because it's a matrix. So it's a determinant. So you're going to take all those partials. You're going to substitute in x naught, y naught. And then you compute the 2 by 2 determinant. So let me just give you a determinant like this. If this is A, B, C, and D, you multiply across that diagonal, you get AD. You multiply across that diagonal, you get BC, and you subtract. So we'll do this times this minus this times that to get the determinant of this. We're going to call this number D. So D is that determinant. Okay, so if you're trying to determine whether a critical point corresponds to a min or a max, this is what you do. First, you calculate D. If D, that's the determinant of the Hessian at the critical value, is positive, that tells you that the second partial with respect to x and the second partial with respect to y have the same sign. Now, if that's positive and the second partials with respect to x and y are both positive, so usually you just check one of them, but if this is positive and that's positive, that means this is positive too. The graph is concave up in the x direction, concave up in the y direction. You put those together, that means at the bottom you're going to have a relative min. So f of x naught y naught in that case is a relative minimum value of the function. Now if D, the determinant of the Hessian at that point, is negative, or excuse me, not negative, positive again, so this is positive, which means these partials with respect to, the second partials with respect to x and y have the same sign. And the partial with respect to x, the second partial with respect to x is negative. So it's concave down in the x direction. And because the D is positive, it's also concave down in the y direction. Those guys have the same sign. It's concave down in the x direction, concave down in the y direction. At the top, you can have a relative max. So f of x naught y naught in that case is a relative maximum. Now, if D happens to be negative, you evaluate the determinant of the Hessian at that point, and you get a negative number. Well, that means these have opposite signs, or maybe one of them's positive and the other one's 0, or something like that. But generally, you don't have both of them with the same sign anymore. If this happens, then f of x naught y naught is a saddle point. So I think the easiest way to think about it is when they have opposite sign. Concave down in one direction, concave up in another direction. So concave up this way, concave down that way. You put those two pieces together and you get something that looks like a saddle, kind of. It's really hard to draw. Okay. Now, if D happens to be 0, usually what you're looking at in that case is an optimum along a curve. So it doesn't look like a min or a max where all of the y values or all of the z values nearby are larger or all of the z values nearby are smaller. And it's not even going up in one direction and down in another direction. Usually in that point, what you have is a min or a max, like on a curve. Like, let's say this is our function. It's a little bit hard to see. So let's say this is our function. So maybe it's just z equals y squared. It looks like this. Well, z equals y squared has a minimum on the x-axis. Z is going to be 0 whenever y is 0. And y is 0 a lot. Y is 0 on a line. Or maybe you have like something that looks like this. So we don't have a min at a single point or a max at a single point. We have a min or a max on a curve like that, or maybe like that. And it doesn't have to be a straight line. It could be like a curve. Like it could really be curving. Like it might, I don't know. It's hard to do that with a piece of paper. Anyway, if the determinant of the Hessian at the critical point is 0, the test is inconclusive. You're going to have to do something else. Okay, now at this point I would love to finish that example that we did earlier, the one that we found the critical points for, but we're really running out of time. The app that I use to record these videos will only give me an hour, which is probably a good thing because that means I can't go on and on. But there's no way we'll be able to finish this problem in the next 15 minutes. So I'm just going to leave you with that. That is the second partials test, and in the next video we will determine if those 5 critical points that we just found correspond to mins, maxes, saddle points, or if we've got a min or a max along a curve, like when the determinant is equal to 0. So that's for the next video.